Okay, so we have this physics problem. It's a small block of mass at 200 g starts at rest at point A, slides to point B where its speed is 8 meters per second. Then it slides along the horizontal surface of a distance of 10 meters before coming to rest at point C. It's asking us what is the work of friction along the curved space, and then what is the coefficient of kinetic friction along the horizontal surface. So the first thing we got to do is you think about the problem and you want to draw a diagram. In this case, in the problem in the book, they gave us a diagram, but we're going to modify it a little bit by adding in some, the ground to make it a lot better than the one the book gave us. So we know that the potential energy of gravity is equal to the kinetic energy, which is 1/2 mv squared, or mgh. We can see the relation in how the energy is like transferred by the conservation of energy. So the potential energy of gravity is equal to mgh. And then when we think about this and we're creating our relation, we have the mgh of point A plus the kinetic energy of point A plus the work due to friction is equal to mgh, which is the gravitational potential energy, plus the kinetic energy, which is 1/2 mv squared at point B. So since the kinetic energy at point A is 0, right, because it's not moving, and the potential energy at point B is also 0 because it's not moving at that specific point, we know that they're 0 and we fill them in. We could basically just simplify what we're trying to solve for, or basically ignore it. So mgh plus the work due to friction is equal to 1/2 mv squared of point B. So now we can solve for part A and rearrange our equation and solve for the work of friction. The work of friction is equal to 1/2 mv squared of point B minus mgh, which is the mass times the gravity times the height of point A. And when we substitute all that values in, we get negative 1.44 J, which the J is joules. The negative, it indicates that the energy was lost or transferred. So it basically became, potential energy became kinetic energy. So part B, now we just carried our diagram and information over. It says, what is the coefficient of kinetic friction along the horizontal surface? When the box slides down and reaches the ground, its gravitational potential energy is 0, which is what we mentioned. So that only kinetic energy remains, like when we talked about, how it transferred. So the energy, since it's lost, it's not lost, it's transferred. So the work done on a system is equal to the change in kinetic energy. It's important to remember that. So the work of friction between point B and point C, which is the smooth horizontal surface, is equal to 1/2 mv squared, the kinetic energy of point C, minus the 1/2 mv squared of point B. When the block reaches point Z, or point C, it's not moving, so the kinetic energy at that point would be 0. So if we substitute that in, we've established now we have the whole relation thing going on. It's kind of simplified now at this point. Now we can solve for what we really want, which we said was the coefficient of kinetic friction, which is negative mu k, because it's going in the negative direction, times the mass times the gravity times the distance it traveled, is equal to the negative 1/2 mv squared of B, which is what we had left over in the equation. So what we have to do is algebraically we can manipulate the equation and be able to solve for mu. Mu k, which is the coefficient of kinetic friction, is equal to the velocity squared of B divided by 2 times gravity times the distance that it traveled. And when we plug all that in, you get it as 0.33. And mu doesn't really have a unit of measure like joules or watts or anything like that. It's just a number. But 0.33, it's quite a bit of friction compared to just on a smooth surface of ice or whatever. It's probably rolling along like asphalt or something that has like a little bit more grit, maybe rocks. But hopefully that explains how this problem is solved, and I hope you enjoyed my video.